Now I will start with chapter 13, and for chapter 13 mainly we are talking about oscillations, and we are going to mainly the main topic is going to be simple harmonic motion, and here we are talking about oscillations about equilibrium. We are going to first introduce periodic motion and say what does that mean, and then what does it mean, like what's very special about simple harmonic motion. We will find that there is a connection between uniform circular motion and simple harmonic motion, and we are going to introduce the relationship between them so that we will be able to use one of the, let's say, one of the motions to describe the other. We are going to study two systems in this chapter. One of them is the mass spring system, and the other one is pendulums are examples on simple harmonic motion. We will also try to solve some problems about energy conservations when we have oscillations. Also, by the end, we will introduce damped oscillations and driven oscillations and resonance. Okay, this chapter is very interesting, but it has so many, I will say, equations that you need to pay attention to. Now, here I have what is really called a mass spring system, where I have simply a spring and a mass. And we are talking about here the oscillation back and forth over the same path. We will find that there is a motion that is repeating itself, and that motion we are going to talk about, which is called periodic. It is one of the systems that we are going to study where, this is here we have the equilibrium position, and then that mass was or like that spring was stretched to the right, and then it was released. We're gonna assume at the beginning that we don't have any frictional forces, and then the mass is gonna oscillate back and forth about the what is called the equilibrium position. When oscillations or vibrations repeat themselves over the same path, it is called periodic motion. Then it is just like repeating itself. There are things here that important parameters that we are going to introduce and talk about. One of them is called the cycle, and the cycle, it is a complete motion from a given point back to the same point. Okay, and here it's very important, for example, to understand if I am talking about, let's say, the mass spring system, just like this is very important. Okay, then if I have, this is my equilibrium, and this is the mass, and it was, let's say, stretched, the spring was stretched to this point, and then that mass is gonna move to the left. It will go past the equilibrium position, and then it will come here, and here it will compress the spring, and then it's gonna come back to the right, and then is gonna start again stretching till it reach this point again. This is one complete cycle. When I talk about the pendulum, then this is, let's say, my equilibrium, then the pendulum, when it's gonna go here and then here and then it's gonna come back, this is one complete cycle. Here there is a misunderstanding always related to this point, and this is the reason why I'm bringing this to your attention. The amplitude, it is the furthest point from equilibrium. This is the maximum displacement here. And it is the same here because we are talking about ideal oscillations. Frequency, it is the number of oscillations per unit time. The wavelength, if we have the scale, the displacement, if we have the displacement versus distance, we are going to say this is like the distance between any two successive wavelengths is gonna be, just here it's not a displacement versus, like if we will just this is like the distance, then this is gonna be the wavelength. Okay, now if we have that scale time, this is gonna be the period. The wavelength is the distance over which a wave repeats, and I will say it is the distance, maybe I have more like sophisticated but more accurate definition. It is the distance between any two successive peaks or any two successive crests. The period is the time required to complete full cycle. There is a relation between period and frequency, and the frequency equals 1 over t, and t, the period, equals 1 over f. T, it is the time required for one cycle, and that is in seconds, and the frequency, it is a number of oscillations per unit time. Okay, the unit for frequency, we can say it is 1 over second, or second minus 1, or it is hertz. A mass on a spring in simple harmonic motion has amplitude A and period T. What is the total distance traveled by the mass after a time interval T? Okay, now, okay, if we will recognize that, let's say here, when the mass was stretched, and then when the spring is compressed, this is A, and this is another A. All right, then when it's gonna be one cycle, it's gonna go A, another A, and going back another A, another A, then it's gonna be 4 A's. Then this is the, okay, the total distance traveled by the mass after a time period of T. Okay. Now, a mass on a spring simple harmonic motion has amplitude A and period T. What is the net displacement of the mass after a time interval T? Of course, it's going to be 0 because I'm talking about the displacement. Here I am talking about the total distance. Total distance, I need to add all the distances here because we are going to say A plus minus A plus A plus minus A, and that is going to be 0. Or we can say when the object is returning to the same point, this means that it is the displacement is 0. Now, a mass on a spring in simple harmonic motion has an amplitude A and T period and a period T. How long does it take for the mass to travel a distance of 6A? We know that 4A is going to take T, and then another 2 extra 2 A's is going to require another half. Then it should be 1.5. This should be the solution. Okay, now you rev your car's engine to 2700 RPM. What are the period and frequency of the engine? Okay, here omega, it is 2700. I can calculate, because omega is 2 pi times the frequency. I can calculate the frequency to be 45. Because omega is 2 pi times the frequency. I need to convert omega into radians per second. And then finally, I will calculate F to be 45 hertz. Now T, it is 1 over F, which is 1 over 45, and this is 0.022 seconds. Now the question is asking, if you change the period of the engine to 0.044, how many RPMs is it doing? Then I will calculate first the frequency as 1 over t, 1 over 0.044 seconds, and this is going to be 22.7 hertz. I can calculate omega as 2 pi times the frequency, and this is going to be radians per second. I need to convert this into revolutions per minute because this is what I am looking for, RPM. Now the answer was 1366, but if you recognize here, we have two significant figures, and this is the reason why I would round it only to have two significant figures. Now, simple harmonic motion, it must satisfy a certain condition. Any vibrating system where the resulting force is directly proportional to the negative of the displacement is a simple harmonic oscillator. What does that mean? This means that here F as a vector is going to be negative, a constant, times X. Okay? That constant here, I want to tell you that, of course, it is positive, and usually it's going to be omega, which is the angular frequency of the system. The minus sign here, it has to do only with the direction. It doesn't mean that the constant is negative. It's telling you that the displacement and the force are in opposite directions. Okay? And this is really very important. Okay, then I have here, this is like the force is going to be in this direction here, and the velocity is going to make the, the spring is trained actually to go to the equilibrium, and then it will go back and forth. And we will find here, this is something very important, that the force is not constant. It is a function of X, then it is changing over time, and sometimes it's going to be 0, and also the acceleration will not be constant as well. Now a spring can be stretched a distance of 60 centimeters with an applied force of 1 Newton. If an identical spring is connected in parallel with the first spring and both are pulled together, how much force will be required? This is just here, we want you to know that when I have a combination of two parallel springs, this is going to be as if we have a stronger spring. Then the force needed here is going to be, for each spring is going to be 1 Newton, then it's going to be a total of 2 Newtons. Always the displacement in simple harmonic motion, it is measured from equilibrium point. Equilibrium point, it is when X equals 0. The amplitude, it is the maximum displacement, and we will use for it A. A cycle, it is full to and fro motion. This figure shows half a cycle. Period is the time required to complete one cycle, and the frequency is the number of cycles per unit time or per second. If the spring is hung vertically, the only change is in the equilibrium position, which is going to be at the point where we are going to have the spring force equals the gravitational force when the spring is in equilibrium. This case is really very interesting. We are talking about a thought experiment that if we have a hole that is drilled through the center of the earth and emerges on the other side, you jump into the hole, what happens to you? Now, when you as an object here, you're gonna, of course, face that negative 9.8 meters per second squared acceleration. But because the mass the mass of the earth as you are moving in, that is going to cause that the gravitational field is going to smaller and smaller, then the magnitude of this acceleration is going to decrease till you will reach finally here where you're going to find all the gravitational forces from all the parts, they're going to cancel. Then you will find that you will go here at this point because of your momentum. Once you are away from the equilibrium point, again, you will be attracted to the earth, and the gravitational acceleration is going to increase till it will be 9.8, and then you will go back and forth in simple harmonic motion. Okay, then you will be in simple harmonic motion. A mass on a spring has a displacement as a function of time that is a sine or cosine curve. There are many experiments where can verify this. And here it is called the amplitude of the motion, which is this here A. Now, an object in simple harmonic motion has the same motion as one component of an object in uniform circular motion. Like this motion here, it is like the motion of the object on the circle, if you project it here, is going to be very similar to the motion of the mass spring system. And this is the reason why we will be able to say omega is 2 pi over t, or it is 2 pi times the frequency. Now, if we wish to find the position as a function of time, because we said it can be described by a sine or a cosine, I can say x equals a cosine theta. And that theta is going to be omega times t. Or, since omega is 2 pi over t, you can write it as this, or you can write it as this. Consider this equation when theta equals 0, x equals a. When t equals t, x equals a, the motion repeats. Okay, then it's just like the motion that we are talking about, which is the simple harmonic motion. If we call the period of the motion t, this is the time to complete one full cycle, and here this is how we can find the displacement at any time. This thing here should be in radians. If you will do that in degrees, this is going to give you a wrong number. Now here we have this one is the top curve is the graph of the previous equation, which is this one, and the bottom curve is the same but shifted 1/4 period so that it is a sine function rather than a cosine. By the way, I can represent it either as a sine or a cosine. It depends on the initial conditions, which means here I can say AX equals A sine 2 pi t over times t. Okay, then it can be represented if the object, like if they're going to give you the coordinate of the object and they're going to say at t equals 0, x was 0, then it is a sine. If the object at t equals 0 was at an x equals a, then we are going to use the cosine. Also, we can calculate the velocity, and the velocity is going to be either we can say the derivative, or we can find it as the x component here, which is minus v sine theta, and this is really the equation. Okay, now a omega here, we call it v maximum. Okay, then according to the fact that the velocity is the derivative with respect to the time, we can do find this equation here. The maximum speed of the mass occurs when sine theta equals 1, and the acceleration, we can say that this is the equation for the acceleration because it is the derivative of the velocity with respect to time. Now, a mass on a spring in simple harmonic motion has amplitude A and period T. At what point in the motion is V equals 0 and A equals Z simultaneously? We don't have that point at all because they are opposite. When the acceleration is maximum, the velocity is 0, and when we have the when we have the velocity maximum, the acceleration is 0. Then none of this, like no point at which both V and A are both having a 0. This is what I was talking to you about. Here we have the position of a mass on a spring is given by this equation. Always you need to know when we compare this with x equal a cosine 2 pi over t times t, that this t is this one, this a is this one. All right, then what is the period t of this motion? Right away you're gonna say it is 8.888 second. Where is the mass at t equals 0.25? Here you are going to substitute with 0.25 for the time. Remember, this should be in radians. You will get negative 1.4 centimeters. I have repeated the calculation with t here equals the period, which is the 0.88 plus 0.25 seconds, which is 1.13, and I got exactly the same number, negative 1.4 centimeters. Here we are given information. An object executing simple harmonic motion has a maximum speed of 4.3 meters per second and a maximum acceleration of 0.65 meters per second squared. Find the amplitude and the period of the motion. We know that Vx, it is A omega equals 4.3. A maximum, it is, here this is maximum also. It is A omega squared, 0.65 meters per second squared. Then I will say A maximum divided by V maximum is A omega squared divided by A omega, and that is going to give you the ratio between them is going to give you the omega, and then from that you will be able to calculate what is really your A. I can also omega, it is 2 pi divided by t. I know omega, I know 2 pi, then I will be able to calculate t as 42 seconds. I'm gonna stop here so that my video will not be very long.